Okay, this is Biweekly Contest 125. About to start virtually right now. Okay, minimum operations to exceed threshold value. So we're given an integer nums, and integer k. In one operation, we can remove one occurrence of the smallest element of nums. Return the minimum number of operations so that all elements of the array are greater than or equal to k. We can remove the smallest element. Okay. So I think we can just sort the array and then iterate through until we reach a value that is greater than or equal to k. So say we have this first example, 2, 11, 10, 1, 3, and our k is 10. So if you were to sort this in ascending order, right, basically we just start our index at 0 and we'll go until our value is greater than or equal to k, which in this case is 1, 2, 3 elements that we'd have to remove. Let's see. So second example, 1, 1, 2, 4, 9, k equals 1. So we start at 0. We're already greater than or equal to k, so we can just return 0 here. The fourth example, 1, 1, 2, 4, 9, k equals 9. So here it's 0, 1, 2, 3, 4. Right, so basically after we're going to sort the array and then iterate our index from the start until we reach a value greater than or equal to k. So nums.sort index equals 0. Do while index is less than the length of nums, and nums index is less than k. We'll return our index. Let's just try all the test cases. 304, 304. Let's try to submit. Alright, so that's good. We'll go to number 2. Okay. So this seems like the follow-up to that first question. Let's read through. So, given an integer array nums and k, in one operation, we'll take the two smallest integers x and y, remove x and y from nums, and then add the min of x and y times 2 plus the max of x and y anywhere in the array. And we can only do this while nums contains at least 2 elements. Okay, so let's look at this first case here. So you have the same as in the first example. So 2, 11, 10, 1, 3. In the first operation, and let's start this just so it's clear what's happening. 2, 10, 11, k equals 10. So basically you would remove 1 and 2, and then add 1 times 2 plus 2 to nums. This would become 4, 11, 10, 3, right? So they add this element right to the start. I'm not sure if that really matters, but I guess we'll see. So in the next step, we would remove 4 and 3, and the value that we would add is 3 times 2 plus 4, which is 10, right? So we have 10, 11, 10. So at this point, all the elements are greater than or equal to k. So basically need to do the operation twice, and we'd be good. So my initial thoughts for this is that we can use a min heap, right? So basically what we would do is store all the elements in our heap with the minimum element being at the top. We would pop off the 2 elements that are at the top. So in this first case, it would be like 1 and 2 first. We'd do that calculation and then just add that back in to our heap. Basically, we keep doing this until the element at the top is greater than or equal to k, right? Because that's the smallest element. If that smallest element is greater than or equal to k, then we know that we've reached that condition. I'm wondering in this case if it's possible that we will never... Okay, so it says the answer will always exist, right? So we don't have to worry about the heap becoming empty or anything. We can just keep going until we find our solution. So let's start a heap, and we're going to import our heap queue library. We'll do for nums, for num in nums, heap queue.heap push heap, and our num value. So heap queue by default is a min heap, so the smallest element will be at the top. We don't have to do anything. And then we'll keep track of the number of operations. What we will do is say while heap length of heap is greater than or equal to 2. Let me just make sure it's actually greater than 2. Yeah, so it's greater than or equal to, as long as it contains at least 2 elements. So we'll do first equals heap queue.heap pop heap. Second equals heap queue.heap pop heap. And heap. So I want to add another condition here just to see if we've reached this point where our smallest value is greater than or equal to our threshold, we don't have to stop. It's less than k, then we can stop. So we have our 2 elements. Then what we want to do is just calculate our new value equals first times 2 plus second, right? So let's do this just to make it clear what we're doing. So we'll have 1 times 2 plus 2. All right, that makes sense. 4 and heap q dot heap push our new heap with a new value. Return operations. Okay, so with our example test cases, we would expect the first test case to give us 2 and the second to give us 4. Let's see if that's what we actually get. 0 and 0. Oh, I forgot to increment my operations. 2 and 4. Okay. Let's try to submit. Okay, perfect. On to the third question. Count pairs of connectable servers in a weighted tree network. Okay, I can already tell, yeah, it's kind of like a graph problem. So let me read through this. So we're given an unrooted weighted tree N representing servers numbered from 0 to n minus 1. As an array edges, connects the edges with a weight. You are given an integer signal speed. So 2 servers are connectable through server C if A is less than B and A does not equal C and B does not equal C. The distance from C to A is divisible by signal speed. The distance from C to B is divisible by signal speed. And the path from C to B and the path from C to A do not share any edges. Okay, there's a lot going on here. Maybe the examples will make it a bit clearer. Okay. So we want to return an integer count of length n, where count I is the number of server pairs that are connectable through server I. Okay. So here, signal speed is 1. Count C is equal to the number of pairs of paths that start at C and do not share any edges. Okay. Let's see here. So server 0, there are 2 pairs of connectable servers, 4 and 5. Okay, I'm honestly like pretty confused about what this is asking. So let's look at this example of 0. It looks like it's saying 4 and 5 are connectable. So why are they connectable? A is less than B. Okay, so if 4 is less than 5, the distance from C to A is divisible by signal speed. The signal speed is 3. So we have 2, 1 is 3, 6, 9. Okay. So yeah, so that would be a length of 9. And also from 4 to 6 would be a length of 6. So that meets the criteria. And then the path from C to B and the path of C to A do not share any edges, right? So what does sharing edges mean? So it can't be like, I guess they can be on the same side of that node, right? Okay, so how do we actually find this path? So we have to start at a node and say So how, like, we need to determine like a left and right kind of thing, right? Because you see here, 4 is on the right of 0, and these two pairs it makes are on like the left side of 0. So try to figure out exactly how this would work. This is a tricky one. Okay. So one thing to consider is that this is also a tree, right? So what does a tree tell us? They could have just told us it's a graph, right? So let me try to draw out some ideas. So what if we took this first case, right, and kind of just drew this out as a tree. So 0, and an edge going to 1, an edge going to, right, and this edge has a value of 1. We'll have an edge going to 2, with a weight of 5. Let's kind of continue down this way. 13. So this should be 3. Have 4 with a weight of 9, and then 5, weight of 2. Okay. So let's see here. So we know that this will have a 0, right? Because this is the root, and there's nothing on the other side that we can connect. So here, what we have to do is say how many nodes that are children can connect with our parents, right? So here, our parents so far are 0. And the criteria that we need to do is say that our root is less than child. And maybe this isn't true. We just know that A has to be less than B. So it could be root less than child, or maybe also the child is greater than the root. The distance has to be, so if the distance from C to A is divisible by signal speed, and distance from C to B divisible by signal speed, right? Does this mean that the entire path, so from B to A, has to be divisible by signal speed? Right? So say we're working with 3, right? Our signal speed is 3. If C to A is 12, and then this is 30, right? We'll get 42. 42 is divisible by 3. So we can simplify this down to the assumption that B mod A has to be divisible by our signal speed. And then the path to C to B cannot share any edges. I think if we try to model this as a tree with a root, if possible, then we can do, like, assume that that's going to be true. So basically here, come here. So far we have our parents. I'm just gonna move this over a little bit to make it a little more clear what's going on. So parents, you will have 0. So we'll say at this point, let's see what children we have that we can make a pair from, right? So if you go down to 2, this is our criteria. Is our root, the value, less than our child? Yes. So what we could do is say that's true. Distance from C to A is 1. The distance from C to B is 5. Our signal speed is 1 because they're both divisible by 1. So we think this is a valid pair. So we can record 1 pair here. So similarly, let's say we're now at 2. So at this point we actually have 2 parents, right? Do we need to check both? I think no, because we can't make this pair, right? We have to connect through a node. We can't connect 2 pairs that are directly adjacent. So we know that we can't make a pair with 1, but we could probably do it with 0, right? So we see the path from 1 to a child of 3 is 13. All our criteria are matching. So I want to look at the second case and see here. So it says this tree is unrooted, right? You know, my tree theory is not great, but I think by definition, a tree has to have some root. I'm wondering if we can do some logic to find that root, like the smallest possible root that we can use to make it easier for us, right? So here it seems like they chose 0 as the root. Maybe we can't make that assumption. Right, and I think if we use 0 as our root here, what would happen, so we have 0. Let's say we have 6. 6 and 3 is our immediate children. Yeah, so we'd have to potentially check these pairs, right? We'd have to go through 0 and connect pairs here. So we could potentially through root. So can we do this in like n squared, where for each we do BFS, DFS, and count the number of nodes we can connect to. So I think if we had like a queue where we keep track, we start at a node, so basically like we have the node value, we have the steps, right? And then we have our path this is the value. Right, so this obviously represents just whatever node we're on. And we'll start at each node. So say we start at node 0, right? What we want to do is say, keep track of the steps. When we reach a node and our steps has to be greater than or equal to 2, right? And what this means is, say we have some other node here, right? If we're starting at 0, our steps here would be 1 and 1, right? So we can't actually connect to these. So we can only connect to nodes that have already gone through another node. And this is just our value. So say we have 1, 3. By the time we get to 5 from 0, we would have 4. Just keep track of that. So the issue is we're not looking for the pairs that we can connect to a node, rather through a node, right? So this kind of makes sense, but it's not going to get us the right answer because we're not looking for how many nodes we can connect to that node. We want the ones we can connect through. So it's almost an idea of we have to have like sides, right? So if we're at 0, how do we determine if these two share an edge, right? Okay, so I think this still might work, right? So if we keep track of nodes that we've seen since starting our breadth first search. Okay, so say 1, I'll put the actual values here. Alright, so say we start at 0, we reach here, right? So basically, at this point, what we can say is, say we first get to 6, then we get to 3. When we get to 3, we can say, I've already seen another node that meets my criteria, right? So 3 is less than 6, and we could check the path value, right? But then what happens if we get to, say, 4 here? Can we do the same logic, right? What's gonna prevent us from hitting 3? We can maybe keep track of the previous value as well and just make sure we don't do that. But I think in this case, it would be valid, right? So we're at 4. We want to see all the other nodes that we've come from, basically. So you could say, all right, well, I can connect to 6 through 0. I can connect to 5 through 0. And any other things on this side, potentially. I think this will work. Let me write out the full graph and we can walk through some examples. We have 0. This goes weight of 3 to 6. This goes to 5. Node node 3 with a weight of 1, node 4 with a weight of 2, and then finally we have node 1 with weight 6. Okay, so let's start at 0. Right, so we'll start at 0. Steps will be 1. We might not need the steps value, but let's see. And 0, right? So then from here, we want to connect our neighbors. So we'll have parent 0. However, we're going to do a check and say, like, is this our root node, right? We don't want to actually connect anything with our root node because we're connecting through. So this will become, we'll have 6, we'll have 1, and we will have our path value is 3. And then we'll also have 3 on here with a 1 step and a path value of 1. So let's say we pop our 6. So now we have 6 in here, right? When we get to 3, we can say, okay, let me look at my parents. Do I have something besides 0 that I can connect with? Yes, we do have 6. Is the two paths divisible by our signal speed? They're not, so they're not a valid pair. So doing this, right, what would happen in the case where we get to like this area of the tree? So say we're looking at like, we visit 3 and then we're looking at like 1 and 2, right? Would we say, like, can I connect through 2? Like, how do we prevent this pair from getting created? Or this pair? Because this actually would happen, because this is divisible by 9. Right, but this is not going through 0. So, I think we need to, like, reframe this as, like, can we every time treat this tree as a tree that's rooted at this value, right? So really, like, these 3 children can come down this way. So it would be like, imagine this is down here. So that looks more like a tree. What if we want to root it at 1, right? So now we have 1 child at 3. Which, this goes to node 3. Node 3 will have 3 other children. So we'll have 2 with a weight of 7, 4 with a weight of 2, and then 0 with a weight of 1, and then 0 has 6, has 5. Okay, so here we don't have 2 children, so we don't really have to consider anything, which maybe that's a good call out, right? 1 child. Is it possible to make pairs through here? I don't think it is. Right, so I think that's a good thing to check. 3 also. So 3 has many children. Actually, let's start with 2. So 2 again has 1 child, so we can't do anything. Let's look at 3. So if we root this at 3, we have 4 children. So we have 0 going to 1. We have 1, the weight of 6. We have 2 with a weight of 7, and we have 4 with a weight of 2. Alright, and then the only other one that actually has children is 0, so we'll have 6, and we will have 5. With a weight of 3 and a weight of 3, right? So basically what we're saying is, do any of these branches, can we make a pair through here? So we have 7 and 2, right? Which seems right to me. So why is this not a pair? Oh, I see. So in the example, these aren't sorted, so our answer is 2, 0, 0, 0, 0, 0, 2, where this value is 0 and this value is actually 3. So 3 would be the other valid case. I don't think what other path there is here. So this is 7, 13, this is 7, 14, 7, 9. So we'd also do this here, right? Okay, so this exercise has taught us a couple of good things, right? We only want to check a tree that has more than 1 child. If it only has 1 child, we cannot possibly make any pairs through it. Right, so I think that'll probably eliminate a lot of cases. The other thing is, now we have to figure out the logic of how do we do this, right? So if we go depth first search and just keep track of nodes, right? So say we get to node 6. We can keep track of 6 and how much it took to get there. So we have 4. Then in our subsequent, recursive call through the tree, we basically say, does any other branch that we visit, do any of these conditions meet, right? If we have 6 with a value of 4, do we have another node that is less than 6 and that meets the other criteria, right? So in this case, we would see yes. So we get to 4 and we say we have 2, 1, 6, and 4 is less than 6, so that counts as a pair. We also have 4 to 5, right? So we have 2, 3, 6, 9, and 4 is less than 5. Okay, so I think that's the general logic I'm going to use here, basically. I'm going to basically convert this tree into an adjacency list with weights. Then for each value in the adjacency list, I'm going to check if it has more than 1 child. If it does, then what I'm going to do is start a depth first search, keeping track of the nodes that I see. when I'm in another branch, I check the other branches that I've already seen, see if there's pairs, and just count those. Right, okay, so this is a bit complicated. I'm probably gonna mess up the code. Let's give it a try. So let's just do our adjacency list is gonna be a default dict. So from collections, default dict. So default dict list, and we'll do for edge and edges. And let me break this down. So we'll do source, destination, and we'll do our weight. So what we can do is say adjacency list source append our destination with our weight, and we'll do the same for S weight, right? So now we have this. Now what we want to do is basically iterate through that adjacency list we just made, right? So we'll do for key neighbors in our adjacency list. We need to check if it has only one child, because if it only has one child, we cannot make any pairs through it. So if the length of neighbors is less than or equal to 1, we can just continue, right? Otherwise, there is the potential to make pairs. So we need to do a DFS, right? So we'd have some sort of DFS function that we're going to do on our root. So what's that DFS look like? Let's try to write that out. So we need to take in our root. We need to keep track of our scene nodes, so we don't kind of get into a recursive loop. And what else? So we know that we only want to consider nodes of the current on different branches, right? So if it's on the same branch, we don't want to count it because we're going to check that case later. So how do we actually check for that? So we could do use another set to keep track of the current branch, right? So as we're going through and we see nodes, we add them in, and then basically we add them into a set that says this is the current branch that we're on, so any of these nodes, do not check them. And then kind of as we come back up the tree, we can remove those from the set. Right, so current branch. So we'll do if root is none, return none. I don't think we're going to get into that case, but better to just be safe. Then what we're going to do is say, also take in our adjacency list here and say for neighbor in adjacency list root, right? What we want to do is say, we want to check our scene nodes. I'm trying to think in what order we should do these operations. If we get to a node, we probably want to check first, right? So let's say for value in scene nodes, if value is greater than our current value, then root, and value not in current branch, then we know we can increment our answer, right? So we'll have an answer that we can increment, right? Then basically what we want to do is then for each one, we'll do our answer plus equals the self.dfs with the neighbor. Let's just break this up. This will be neighbor weights with our neighbor. Okay, so still just kind of thinking through this. So we might also need to keep track of the path length here. Path length, right? And then we'll do scene nodes. We could pass in all these arguments, obviously. Current branch, and then path length plus weight, right? So I think before we do this, what we want to do though is say current branch. We want to add our root, right? And what that's doing for us is saying that the branch that we're on, we don't want to check against any of those nodes. But at the end, will be current branch dot remove. Right, so basically this current branch, set is basically keeping track of the state of the tree and where we are. The only other issue I see here is that we need to also keep track of the value, right? So we need to have, let's say, previous node and value, right? So if the previous node is greater than the root and value not in current branch, and our path length plus value, and maybe let's call this previous path, just so that we keep track of it. We'll say plus value mod signal speed equals 0. And then we can increment that, right? So we're also going to need our signal speed here. Right? Okay, and then at the end of this, what we're going to do is just return our answer. Okay, so let me just redo this. So if the root is none, we return, right? That's fine. We're going to start and say our answer is 0. What we want to do is say, for all the previous nodes that we've seen, if the previous is greater than the root, which is our one condition, and the value is not in our current branch, and the length that we've taken to get here, and the length we've taken to get to value divided by the signal speed equals 0, we know we have found a valid case, right? Then we want to check all the neighbors. So basically then what we're saying is we're going to keep track of the current branch, go down through here, and then remove this. Okay, we have a solution object. So let's just keep track of the count, all this counts. And this is going to be an object where when we get this answer, we're going to say counts key equals that answer, right? And then let me print counts here, just return an empty array. I want to see if we actually get the right thing. DFS is not defined. Should be self DFS, and we have to pass in all these arguments, right? So we have to pass in a hash map, a set, our adjacency, list, 0, signal, speed. This is taking a very long time. Okay, I'll do if root. Yeah, I'm getting a recursion stack overflow. So if root in scene nodes, just return. Let's try that. Okay. Okay, so I'm never adding my value to scene nodes, right? So scene nodes root equals path length. That should take care of it. Cannot unpack on iterable int objects in scene node items. They're trying to clear up all these errors here. There are a lot of them. And plus previous. Okay, so hopefully that's all of them. Let's run the code, make sure it just runs. Int and none. So let's return 0. Return 0. Okay, so here I'm getting nothing. Here's 0, I'm getting 3. Alright, so totally wrong. Let's look at this first case, right? So I'm getting, I feel like I'm never even considering the other ones, right? So 0 I can't consider. 1. What are we getting? So for 1, I'm getting 0 when I should be getting 4, right? So why is this happening? So, So I'm just trying to think through where my error might be, right? Because we know if we're at one, like we're checking the right nodes, right? We're checking all the ones that don't have one parent. And I'm just not finding the pairs. So maybe here, let's say if root equals 1, print or root is less than previous node. Let's try this. Okay, so I was thinking maybe it's like dependent on the ordering, right? Like which we do first. Okay, so we only have one. Okay, that's not quite right. Let's see. Trying to think through, right? So I'm imagining in this case, like if we do this path first, and then we come to 1, 0, right? We never register that we can connect maybe we need to sort this. Let's do for key neighbors and edges. We can do adjacency list key equals neighbors. So what I'm thinking is like the ordering actually is important here, right? We want to make sure we're visiting the smallest ones first because we're checking if previous node is less than our root, right? So if we visit the smallest ones first, that will help us. Too many values to unpack. And sorry, there should be also adjacency list items. 1, 4, 2, 6, 2, 6. All right, so are we getting? Okay, we're getting it. That's good. Okay, and then 0 is 3, 6 is 3, 3 is 2. That's not right. That is definitely not right. So maybe we'll need to keep track of pairs we found, right? So let's do found pairs. This is just becoming like a mess here. We'll do found pairs. So we'll do if previous node root not in found pairs, then we'll say answer plus equals 1, but then to found pairs, we will also add previous node and root. So I'm just hacking things together at this point that don't really make a lot of sense. Found pairs, and then found pairs. Okay, so we're getting 3 there. it's still not right. And this, now that made this worse, right? So okay, so this should be 2, this should be 0, this should be 2, so that's right. Okay, so why for 6? Why are we getting this right? So 3, 3. So why can't we connect 0 and 5? Am I missing some condition? So A is less than B. That's very interesting. Oh, wait, so okay, so my initial assumption was wrong. So let me update this. So I think my path logic was wrong here. So if path length mod signal speed equals 0 and previous path mod signal equals 0. Okay, let's see if that changes anything. 2, 2. Okay, I think that looks good. Okay, and then basically what we have then is saying we have our solution, right? So solution is this, and then we'll do 4 counts for key value in counts.items. Actually, let's do index. So we'll iterate through all the indexes. So sorry, feeding myself. So let's see for I in range edges. Basically, what we want to do is say if I in counts, then we'll do solution dot append counts I else solution dot append 0 and return the solution. What happened? The list object cannot be interpreted as integer. Now it should be length of edges. Length of edges plus 1. Okay, so these 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so this is looking correct. This 04664, 04664. Okay, I'm gonna try to submit this. Good chance I'm gonna get a wrong answer or TLE. Yeah, I think it's gonna take too long. Okay, wrong answer. Let me just screenshot this. Okay, so so one thing I'll notice is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so they're the same length, but clearly our logic is just messed up here. So what could be happening? Right, so maybe we can try to draw this out. So we have 1 going to 0, 2, 2 connected to 1 with a weight of 4, 3 connected to 2, with a weight of 4, 4 connected to 0, with a weight of 3, 5 connected to 1, with a weight of 4, 6 connected to 2, with a weight of 2, 7 connected to 6, with a weight of 4, 8 connected to 1, connected to 1, with a weight of 1, then 9 connected to 8, 8 with a weight of 3. Right, so let's look at our answer here. Okay, so clearly for so this should be, this first number should be 0, right? We're looking at 0. It's going to be difficult to actually count all these pairs out. Our signal speed is 1. So basically what we could say is we can connect this one to all the other ones on this side. So we'll do 1, 2, 3, 4, 5, 6, 7, 8. Right? So why am I getting 17? Right? That's kind of the question. Just trying to think through this. So if I'm at 0, am I potentially also counting? Oh, maybe I'll keep track of my parent, right? So the parent, let's do if previous node equals parent, continue. Right, and then our parent is our key, and we'll just pass that down to key. Let's try this. Sorry, it should be parent here. Okay, so I'm still getting the same answer, so that's clearly not it. I wonder why I'm like double counting. So I think that's what's happening, right? I'm clearly double counting and then even adding 1 on top of that because we expect to get 8, but I'm getting 17, right? So let me do if previous node equals parent. Let me just print our scene nodes. Let's see what's going on. So we've gone all the way through. Okay. Let's see. This is a pretty difficult problem. So, previous. So 0 and 2. So this is interesting. So it looks like to me, I didn't fully explore this one path, right? I went from 1 to 0 to 4. I'm doing a DFS, so I would have expected I would fully explore this one path first. So is there just like an issue with my recursive function here? So we start at 0. Start at 0. And start at 0 and go to 1, right? And then from 1, I would expect us to visit the rest of these, right? So we'll do for 1, for neighbor, wait in. So we come here, fruit is none, or fruit in C nodes returns 0. Oh, maybe we need to add our let's see how much time we have left in this contest here. 15 minutes. All right. So I think something is going wrong with my solution here, where it seems like I'm not actually doing the recursion that I want. So I'm exploring 1 first from 0. Or maybe am I starting? Oh, I'm starting at 1. If I print out my counts, am I ever doing? Print my key. I see the order I'm actually going in. I'm starting at 1, 0, 2. Like, that shouldn't really matter, right? Like, these are all scoped.
That number is used in some locations for emergencies.
So these are all scoped to each function call, right? So there's no reason why they should be like interfering or anything like that. Let me at the end print counts. Huh. This is definitely tricky. Alright, so 0, starting at 0, we're going to 1. Yeah, so it looks like in this case we are fully exploring all of those before we hit this, right? So, pre-node equals parent. I want to continue. Previous node is less than root, and previous node is not in current branch. And okay. So what is happening? Root. So we're going through all the neighbors of our root. We're passing in that new neighbor with our scene nodes. If root and scene nodes, right, so we're not repeating any, like from 0 here, right? Let's print our current branch. Let's look at 0, 1. We're starting at 0. I'm gonna actually make this a bit more easy to read. For 0, current branch is 0, 0, 1, 0, 1, 2, 0, 1, 2, 3, 6. Okay. Right. So the leads are not in the current branch. So 0, 1, oh, it has to be on the opposite side, right? Because I see. So these are getting counted. So I think what's happening is, say we go to 1, right? We count this as our current branch. However, when we get to this, back to this 1 from this DFS, all of these nodes are counting the nodes on this side, right, as nodes that they could potentially pair with, which for our logic is wrong. We do not want that to happen. But I think the question is, how do we actually prevent that? So, how do we prevent this? So I think we need to fix our current branch logic, right? We need to say, if these, if they have the same, like, ancestor, right, which being the child of the root, right? So say we're looking at 0, it has 2 children, 1 and 4. All the nodes here have the same ancestor in 1, so we cannot possibly connect those. Right, but how do we keep track of that? So what if for each key we do, instead, iterate through the children, right? So we'll say basically get all the children and say, here are the children, how long it takes to get there. We can actually do this for each child, right? So say we have 3 children. We go through the first one, get all the children and their paths, save them, right? Then basically what we do is we go to the second child, we get those, but we compare those to the first one, right? And then basically we just count the pairs, add those in there. So I think that might work. Okay, so let's do this. We'll do key counts equals this. Let's do right, okay. And then what we want to do is scene nodes equals this, scene nodes, and then basically we'll do our master object equals this, and we'll do let's see, so we'll do for key value in scene nodes items for master key master value and master object. You can do say if key is less than master key end value mod signal speed equals 0 and master value mod signal speed equals 0. We can do counts key plus equals 1, and we'll do for key value in scene nodes items. What you can do is say master object key equals value. Okay, let's see. Master object, but this doesn't make any sense either, right? Because we're not doing so let's see 0, let's okay. More steps. Alright, no, this is not gonna work. This is not working. Alright, well, I have 2 minutes left. I think it's unlikely that I'm gonna solve this right now. So thanks everyone for watching. I'll solve these problems and upload them later in the week. Bye.